Everybody, in this last couple of videos, we've been discussing the parent functions and kind of what they look like. They're pretty basic characteristics of their graphs and domains and ranges. But in this series of videos, we're going to start discussing how we can transform these graphs. Okay, and an understanding of transforming graphs is actually really going to help us understand many different functions that are put in front of us graphically, even in our heads. Just kind of the basics of what it's going to look like. Okay, so we're going to start with what we're going to call rigid transformations. Okay, rigid transformation, and specifically what we're going to be referring to is translating graphs. So if you remember from geometry, translating meant no more than what we're going to be doing is taking an original thing and shifting it either left or right or up or down in the xy coordinate plane. Okay, so what we'll do is we're going to go ahead and start with this function right here, this parent function. This is one that we're very familiar with, or should hopefully be familiar with. It's the squaring function. Okay, but the squaring function, some unique characteristics of the squaring function. Maybe we switch colors here. We go a little bit more standout. Okay, it has an intercept at 0, 0. It proceeds up 1 and right 1. Okay, there's y-axis symmetry, so it is a parabola, and goes left 1, up 1, or up 1, left 1. But we say, okay, so here's the graph of f of x. I'm going to put, oh, I don't want that color. We don't want that color. We say, okay, so this is f of x right here. Okay. What I'd really like to do is analyze not this graph, but a couple of other functions. So let's go ahead and call another function. We'll say it's g of x. Okay, and g of x in this instance, we're going to call it x squared plus 2. Okay. So one good thing maybe to do is to look at a table of how this would necessarily be different. Okay, in the last graph, you know, it went. We could say we plug in some x values here. You know, it would have necessarily at 2 been up at a height of 4. 2 squared is 4, and negative 2 squared is 4 as well. But we've got this graph right here, so we're going to go ahead and use the same x values when we evaluate this one. So let's go ahead and use negative 2, negative 1, 0, 1, and 2. And if you're clever, you've already figured out what's going to happen here. But when we plug in negative 2 for this x value right here, negative 2 squared is 4. We're just going to tack on 2 to it. Okay, so we could almost call this 4 plus 2, you know, but we'll go ahead and list it as 6. We say negative 1 squared. Negative 1 squared, in the last function here, when we plugged in negative 1, it went to a height of 1. But this would be like that height of 1, or that negative 1 squared, plus another 2. Okay, so we've got 3. 0 squared plus 2 would be 2. 1 squared is 1, plus 2 is 3. And then 2 squared is 4, plus 2 is 6. Okay, so this graph's going to look slightly different. And when we sketch this one, you'll see what it looks like here. I'm going to start with when x was 0. I like to start with intercepts. But when x was 0, we're at a height of 2. When x was 1, we were at a height of 3. Okay? When x was negative 1, we were at a height of 3. But what I want you to see is basically this. I'm not going to, you know, draw this in perfectly here, but we're going to call this here, we can say this is g of x. But you're going to notice compared to the original function, you'll notice that it shifted, and it shifted specifically up 2. So it's no shocker that it did this, and it's no shocker, rather, that it's at a plus 2 tacked onto the end of this, okay? So that's f of, or g of x equal to x squared plus 2. So almost like the original function here, plus 2 more. What I would like to do is take this a step further and really point out that this is x squared plus 2, but since x squared, okay, x squared was equal to f of x in the first place, that's almost like we are saying this, f of x plus 2. And when we added 2 on to the original function, okay, what it did was it took the original pink function here and shifted it up 2. So we're going to leave that one for now, and let's switch colors again here. I don't want to go pink. How about we go like a blue? There we go. And we're going to call this one h of x. And instead of adding 2 on the outside of the function, I'm actually going to play around with this one here. I'm going to call this x minus 2 quantity squared. Okay? So when we graph this, and you're going to be like, oh, why are you choosing those x values? Well, I've kind of got a reason behind my rhyme here, but let's choose, let's say 0, 1, 2, 3, and 4. Okay, so let's say we did plug in this x value of 0 right here. We say this is 0 minus 2, that's negative 2, but negative 2 squared is 4. Okay, if we plugged in 1, so we'd have 1 here for this x value right there. 1 minus 2 is negative 1. Negative 1 squared is 1. And then 2, plugging in 2, you'll see real quick that 2 minus 2 is 0, and 0 squared is 0. This is actually, this x value right here is a 0 of this function. When we plug it in, we get a height of 0. And then just real quick, we'll talk about 3. 3 minus 2 is 1, and 1 squared is 1. So you notice this function behaves a lot like our first function up here, x squared, except for its x values have necessarily been altered because of the fact that we were messing with this parenthetical quantity that itself was squared. Okay, so we didn't square the x individually, we squared x in a difference with this 2. And so here's what happens. We say when we plug in 0, 4, 0, 4 is necessarily going to look like 0, 1, 2, 3, 4, height of 4. Okay, 1, comma 1. So it's got this point here. 2, comma 0. And we had 3, comma 1. And then 4, comma 4. So now we've got this parabola right here. And so, you know, I've got a lot going on up here. This was h of x. But what I want you to notice here is this graph, when we graphed h of x equal to x minus 2 squared, it actually shifted the original pink graph 2 to the right. Let me say 2 to the right. Contrary to the fact that it said minus 2. So what I really want to do is I want to kind of think about what this says right here. We have something squared, okay? Let's take into consideration the original function, which was f of x equals x squared, okay? If we had necessarily done this, we say, okay, so here's what I want to do instead. I want to plug in f of x minus 2. If we had done that, we'd say everywhere we saw an x, we'd take it out, okay? And we would plug in x minus 2. So the interesting thing here is that f of x minus 2 is actually equal to h of x. So here's the thing about it. We say h of x is actually equal to f of x minus 2, which caused the original function, okay, so f of x minus 2 with this 2 on the inside here. The last time we considered this other function here, we said f of x and then on the outside plus 2. In this case, the 2 is being considered on the inside of what we're calling f, and it shifted it 2 to the right. So what we'd like to do here is really just kind of generalize what we see going on. And so in order to generalize this, you know, we're just going to talk about how these other constants here, either on the outside of f of x or the inside of f of x, alter an original graph. So what we're going to do is we'll define this like this, okay? So we say, how about what if we had some function h of x? Translations. And h of x is actually equal to some original parent function f of x, but we say, how about like plus c? What this does is it shifts, okay? Shifts vertically, c units, and in this case, up. So it takes this original f of x and shifts it up however many units, c here, into the air, okay? What if we had another function, we would say h of x, you know, different than the first one here, but h of x in this instance is f of x. In this case, we subtract a constant, okay? This is also going to shift it vertically. Shift vertically. Vertically. But we're going to go c units, down. So you'll notice whenever we have like an original parent function, f of x, and we're on the outside of it, we add c or subtract c, what we're really doing is messing with what we call vertical translation or vertical shift, however many it says, okay? A little bit different from this. We'll go with h of x. We say we're given some function h of x, and what it looks like is some parent function. But this parent function, say plus a c, but you notice the c is on the inside of this parenthetical quantity now. What this does is it shifts it, but in this case it's going to shifts horizontally. Okay, so this one shifts horizontally, and I want to put in a caveat here. Whenever you're dealing with the c value on the inside of here, it's always kind of opposite of what the operator would lead you to believe it's doing. So you would say, oh, this is going to shift horizontally c units to the right in a positive direction because this was a plus. It actually shifts c units to the left. Okay? So when we're dealing with these things that we're plugging into this parenthetical quantity, we're not going to believe what this plus sign actually says. Okay? And then last but not least, the last case here, and then we'll go ahead and move on to another video. But we say, to kind of supplement this, f of x minus c being plugged in, this is going to shift horizontally. Okay, shift horizontally c units, and this one is actually going to shift to the right because the sign on the inside here suggested that it was negative. Okay, and we'll just, for right now, we'll remember that as being backwards.